Hello and welcome to another lecture of ECE 108. In this lecture, we're going to continue off where we left off in lecture 1 and examine some new logical connectives. So first, we're going to define what I mean by a compound statement. So a compound statement is going to be a statement that's composed of several individual statements, each of which is called a component statement. So in this course, we're generally going to consider two types of base compound statements: and statements and or statements. An example of a compound statement is, we will go to the park and have lunch. So a natural question to ask is, when is this statement true? So pause the video and think for yourself when this might be true. This will be true precisely when we go to the park and also have lunch. Both of these individual component statements, we go to the park and we have lunch, need to be true at the same time. So when would this be false? Well, this would be false if we do not go to the park and or we do not have lunch. We only need one of these two statements to be false in order for this compound statement to be false. So let's look at another example. We will go to the park or have lunch. So when would this be true? Well, this would be true when we either go to the park, have lunch, or go to the park and have lunch. So notice that the use of or as a logical connective is a bit different than the use of or in your day-to-day life. Namely, the compound or statement is true when both of the component statements are true. So we call the standard or that you'd use in regular English exclusive or XOR. So to be concrete, if I asked you soup or salad, you could say both, but that's not what the waiting staff mean when they ask you soup or salad. They mean one or the other. So do keep this difference in mind when working in this course, as that is a common point of confusion. So now, when is this statement false? Well, this statement will be false when both of the component statements are false. So explicitly when we do not go to the park and when we also do not have lunch. So now let's formalize these ideas a little bit. So the compound statement P and Q, written as P wedge Q, is called the conjunction of P and Q. And the truth table of P and Q is, well, let's work through it. We know that we have two component statements, P and Q, therefore we're going to have 4 rows in this logic table, and let's go through them. So if P is true and Q is true, then P and Q will be true. But if at least one of P or Q is false, then P and Q will be false. So the rest of these elements will be true, false, 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 true, false, and false, false, false. So notice that when I build these logic tables, I use a kind of pattern when I'm writing out the possible values of P and Q. I first start with P being true and then switch between Q being true and false, and then I consider P being false and switch between Q being true and false. That's a good pattern to use, and later in this lecture, I'll show how that pattern generalizes when you have more than 2 component statements. So let's look at a few examples of conjunction. So are the following statements true or false? Dogs are animals, and 4 is greater than 3.9. So pause the video and see what you think the answer is. Well, dogs are in fact animals, and 4 is in fact bigger than 3.9. So since both of the component statements are true, this statement is true. Next, lawyers are not cats, and the square root of 2 is irrational. So pause the video and decide whether or not you think this is true or false. Well, are lawyers cats?
Here live, I'm not a cat.
Okay, so lawyers aren't cats. Is the square root of 2 irrational? Well, the square root of 2 is irrational, but since lawyers are not cats in the truth table, we're at this entry, therefore this compound statement will be false. Now let's look at disjunction. So the compound statement P or Q, written as PVQ, is called the disjunction of P and Q. So the truth table for this will simply be written as follows. So again, I'm going to have 4 entries to this table. And if P is true and Q is true, then P or Q would be true. In fact, if one of P or Q is true, this would be true. So in this line and the next line, we get true. But in this last line of the table, I have P is false and Q is false. And if both of the component statements are false, P or Q would then be false. So let's examine a few examples of this. Are the following statements true or false? Dogs are animals, or 4 is less than 3.9. So pause the video for a second and see what you think. Well, dogs are animals, but 4 is not less than 3.9. Therefore, we're at this entry in the truth table for P or Q, and the statement is thus true. So one more example. Lawyers are not cats, or the square root of 2 is irrational. So pause the video and see what you think. Well, again, lawyers are not cats, and the square root of 2 is irrational. So in this case, we're in this column here, true, 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 therefore the statement is true. So now let's look at another logical connective. Explicitly, let's look at implications. The statement P implies Q, written symbolically as P right arrow Q, is called an implication. So the component P is referred to as the hypothesis of the implication, and the component Q is referred to as the conclusion. So the truth table for P implies Q is going to be this table here. If P is true and Q is true, then P implies Q, we'll say that's true. If P is true but Q is false, then we'll say that the implication P implies Q is false. And finally, if P is false, we'll just say that the implication is true. So let's think of why we might want to use this as a truth table for implies. So let's use an analogy. So an implication statement is like a promise. So if I promise you that if you do P, then I will do Q, what are the possible truth values of whether or not I kept my promise? Well, if you kept up your part of the deal and I did what I promised you I would do, then I upheld my promise, therefore the implication would be true. But if you kept up your part of the deal, but I didn't do what I promised to do, then I did not keep my promise. On the other hand, if you don't keep up your part of the deal, it doesn't matter whether or not I kept up my part of the deal. I'm not violating my promise, so I trivially kept my promise. Now notice that if the hypothesis of an implication is false, then the implication is true no matter the truth value of Q. This is what's called vacuously true. So now let's look at a couple of examples of implications. So if x is greater than 2, then x squared is greater than 4. So I can ask a few questions. What's the hypothesis of this implication? Well, the hypothesis would be that x is greater than 2. What's the conclusion? Well, the conclusion is x squared is greater than 4. And is this true or false? Well, if we think about it, if x is greater than 2, when I square it, I'll get something that's bigger than 2 squared, so I'll get something that's bigger than 4. So in this case, this would be a true implication, and in particular, it's true in the non-vacuous sense. So I'm sitting here at this true, true, true case. So one last comment, if you want to prove an implication, it's sufficient to show that if P is true, then Q is true. This is simply because in the case where P is false, the truth value of Q does not matter. And if P is true, I need Q to be true in order for the implication to be true. So just keep that in mind going forward. Okay, now let's look at inferences. The statement P is inferred by Q, written as P left arrow Q, is called an implication or an inference. So the truth table for P is inferred by Q is going to be quite similar to the truth table for implications. So if Q is true and P is true, then I have true. If Q is false and P is true, I have true vacuously. And if Q is true and P is false, I have that the inference is false. And finally, if Q is false and P is true, I have that the inference is true vacuously. Notice that this is just a different but useful way of writing Q implies P. So explicitly, I just kind of swapped the P and Q and swapped the direction of the arrow. So here, I won't go through an example of inference. If you have questions, you can ask on Piazza or during office hours or tutorials. But inferences are simply implications going the other way. Okay, now let's look at if and only if. We say P if and only if Q, written symbolically as P left right arrow Q, whenever both P implies Q and P is inferred by Q are true. So if I want to find the truth table for if and only if, how would I do this? Well, let's build the truth table by hand before I show you the truth table explicitly. So here I want to build the truth table for if and only if. So I have two component statements to consider, P and Q. So let's draw a table. Okay, so here I'll put P and over here I will put Q. So the possible truth values of P and Q, well, P again can be true or false. And if P is true, then Q could either be true or false. And if P is false, then Q could either be true or false. So now I know if and only if is true, precisely both when P implies Q and P is implied by Q are true. So let's build a truth table for P implies Q and P is inferred by Q. So to do this, recall that our table for P implies Q is what exactly? When both P and Q are true, then P implies Q is true. When P is true but Q is false, then I broke my promise, so P implies Q is false. And when P is false, then it doesn't matter what the value of Q is. I didn't violate my promise. Okay, so further, what is the truth table for Q is implied by, or P is implied by Q? Well, if Q is true and P is true, then that inference is also true. If Q is false, then it doesn't matter what P is. I have vacuous truth. If Q is true and P is false, then the inference will be false. And if Q is false, then again, it does not matter what P is. Okay, so now to build the truth table for if and only if, I need to build an entry in this table where this statement is true and this statement is true. So explicitly, to use our symbolic notation, I need to build the truth table for P implies Q and P is inferred by Q. So now, when is this column true and this column true? Well, looking down the line, it's true for this case. It's false for this case because this P implies Q is false. It's false for this case because P is inferred by Q is false. And it's true in this case. So the truth table for P if and only if Q is given by this column here for P, this column here for Q, and this column here. These extra columns that I built in the middle are how I can prove that this is the truth table for if and only if. So going back to the lecture slides, this is the truth table for if and only if, which is exactly what we wrote. So now before we go further, I want to define logical equivalence. If two statements have the same truth values for all possible values of the statement variables, then they are called equivalent statements. Further, if two statements are equivalent, then you can say statement A, if and only if statement B. So for instance, we could say P if and only if Q, in parentheses, if and only if this statement here, because by definition, these two statements are equivalent. So further, we can use this triple equals to denote equivalent statements. So in the course notes, they use the double arrow to denote equivalent statements. I prefer using the triple arrows, but there are valid reasons to use both notations. So I'll leave it up to you which notation you wish to use. But just keep in mind that there are these two equivalent notations you can use. Now, let's look into proving compound statements via truth tables. So in the previous slide, we basically did this for if and only if, but let's kind of go through a few more examples to show you how to use this in general. So show that if P is a statement, then not P is equivalent to P. So this is kind of the idea that you've had when you're like, I'm not it, or I did not do it. It's the logical equivalent of that type of statement. So how would I prove this statement? Well, instead of just giving you the truth table, let's derive it. Well, here I want to build a truth table having all of the possible truths for P, so let's draw a table real quick. So since I only have one statement variable, I'm only going to need two columns. So P is either true or it is false. So what does this mean in terms of not P? Well, that means not P is going to be false when P is true, and it's going to be true when P is false. Just the definition of negation. Therefore, not P, what would its truth values be? Well, not P will be true when not P is false, and not P will be false when not P is true. So now if I look at these two columns here, they have the same truth value for every column in the truth table. Therefore, P will be equivalent to not P. Now, I will note in your text, they explicitly write another column in the truth table. Explicitly for this case, I would have P if and only if, not P. And they would write out the truth values here, which will be true and true. That's not explicitly required, given that you explicitly state that the truth values of the two statements you wanted to show were logically equivalent are the same for every row in your truth table. You can do this extra step if you want, but I'm not going to require it for this course. Okay, so now that we've done that, we know that this is the truth table that we need, and thus, since not P and P have the same truth values for all possible truth values of P, then not P is equivalent to P. So if I were to ask you to prove a statement, I would want to see a proof like this, or alternatively, again, you can add that fourth row to your table, or extra row to your table, and comment that that statement is true, therefore the statements are equivalent. So it's up to you which one you prefer to do. Okay, let's look at another case. Prove that not P and Q is equivalent to not P or not Q. So how would we do this? Well, we need a truth table. So let's go back and draw this truth table. Well, since now I have a P and a Q, I'm going to need 4 lines in my table. So let's draw 5 lines here. Okay, so here I'm going to have P, and P will either be true or false. And in the next row, I will have Q, and Q will either be true or false. So we get our standard enumeration here. So now going back at what I want to prove, I explicitly want to prove this statement. So just for convenience, let's put this up here. So I need to compute 2 statements. I need to compute the left-hand side and I need to compute the right-hand side. So how can I break these statements down into something that I can compute via a truth table? Well, let's just focus on the left-hand side to start with. So here I have this P and Q. So let's just build the truth table for P and Q. So if I did that, I would have P and Q, and what would we get? Well, the statement P and Q is true precisely both when P and Q are true. So filling out the truth table, I will have true, false, false, false. Now, in order to build the left-hand side, I need to build this negation. So to do that, let's just negate this row of the truth table. So not P and Q will simply be false, true, true, true. Now, looking at the right-hand side, I need to build not P, not Q, and then I need to build the row for and then I'll be done. So when doing a proof like this, I find it useful to leave kind of a double space thing like this, just so that you're kind of clear, I'm done with the left-hand side, I'm now working on the right-hand side. Okay, so let's build the truth table for not P. So not P will be false, false, true, true. And for not Q, I'm going to simply have false, true, false, true. Okay, so now I want to build not P or not Q. So I simply want to take this column or this column. So let's build that. Well, false, false or false, that's just false. False or true, that's just true. False or true or false, that's just true. And finally, true and true, that's true. So now if I look, here I have that this column, which represents the left-hand side, has the exact same truth values as this column, which represents the right-hand side. Therefore, these two statements will be logically equivalent, or alternatively, you can build an extra row saying left-hand side if and only if right-hand side, and then you'll get true, 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 and true. Therefore, we would get that these two statements are logically equivalent. Okay, so notice that, and again, here's just my truth table filled out. So thus, since not P and Q and not P or not Q have the same truth values for all truth values of P and Q, then I have that these two statements are logically equivalent. So now this statement that I just proved has a name. It's called De Morgan's Law. And in particular, there's another De Morgan's Law negating the statement P or Q. So I will leave this as an exercise. I strongly encourage you to actually do this exercise. Okay, so let's look at one more example. Use truth tables to prove that P implies Q is equivalent to not P or Q. So for this case, note that this would be the truth table for this P implies Q and not P or Q. So explicitly here I just used the truth table for P implies Q. Here I just negated this P, and here I simply took this column or this column. So here the truth values are the same between these two. Therefore, these two statements are logically equivalent. So this statement is quite useful because it means that implications are equivalent to statements that do not involve implications. In particular, this can give you a new proof technique to prove implications. Instead of assuming P is true and showing that Q has to be true, you can instead prove that not P or Q is a true statement. Okay, let's look at one more example. So here I will go through all the details for this case. Since you're watching a video, if you don't want to see the details, you can skip it, but I will make it available for those of you who want to see it. So if I wanted to prove that this statement is logically equivalent to this statement, how would I go about doing that? Well, let's go to the whiteboard. Notice that there are now 3 statement variables in this problem: P, Q, and R. Therefore, when I go to build the truth table, I need to have 2 to the 3rd or 8 entries to the truth table. So let's go ahead and draw 9 lines. Okay, so the first 3 columns are simply going to be P, Q, and R, and we need to go through all of the possible values of P, Q, and R. So how can we go about doing this? Well, a common standard way of building truth tables for arbitrarily many statement variables is to simply start by writing the first statement variable as true for 2 to the number of statement variables in the problem minus 1 entries, and then false for the other half of the entries. So let's do this. So here I will have P, and in my columns I will have true, 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 false, 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 and false. Okay, so now we can see all the tables here. So next, for Q, I'm going to simply alternate between true and false, but since I have one more statement variable, Q will act like P did in our previous truth tables. So I'm going to have true, true, false, false, and then true, true, false, false. Finally, for R, I simply alternate between true and false for all of the columns. Okay, so now if you noticed, this goes through all of the possible truth values for P, Q, and R. And to help keep this separate, I'll do a double line here. Now I need to build the entries in the truth table for the left-hand side and the right-hand side of the supposed equivalence. So how do we do this? Well, I'll start with the innermost parentheses. So I'll start here on the left-hand side and I will write P or Q. So what are the values of P or Q? Well, just going down the list, P or Q will be true when either P is true or Q is true. So these first 4 entries, I will have truth because P is true. And for these next 2 entries, I will have truth because Q is true. And finally, for these last 2 entries, I will have false because both P and Q are false. Okay, so now I want P or Q implies R. So we can now write this out by using this column and the truth table for implication. So explicitly, we will have that the truth table for P or Q implies R will be as follows. Well, for this first column, I have true implies true, so this will be true. For the second column, I have true implies false, so this will be false. Next, I have true implies true, so that's true. True implies false, that's false. True implies true, that's true. True implies false, that's false. And finally, the last two, the hypothesis is true, so I will simply have true and true. Okay, so this is done with the left-hand side. Now I need to build the right-hand side. So how do I do that? Well, just looking at it, I can first notice that I have these two statements here and this statement here. So I can build the truth table columns for those two statements, and then I can finally build the truth table entry for this third compound statement. So P implies R. So when would this be true and when would this be false? Well, for the first entry, P is true, R is true, so this is true. For the next entry, true implies false, that is false. The next one's true implies true, that is true. The next one, true implies false, that is false. And the last four, the hypothesis is false, so I have that it's trivially true. Okay, so now I need to do the same thing with Q implies R. So for the first line, I have true implies true, that's true. True implies false, that is false. False implies something, so that's always true. Same for the next line. True implies true, that's true. True implies false, that's false. And then again, the hypothesis was false, so I get trivially true. Okay, so now I have everything to build the last step. So here I want to know when is this true and when is this true. So it'll precisely be true when both of these statements are true. So here I get true. So for the first column, I get true. For the second column, I get false, true, false, because this one's true, or false, true, false, true, and true. So now I can notice that this column is false precisely here, here, and here, and this column here is also false precisely on those three entries. Therefore, these two statements have the same values in the truth table, and therefore they are equivalent. So again, I could write this if and only if this and write that in the table, but it's up to you which one you choose to use. So you can tell that truth tables become tedious quite quickly. For instance, if I had a statement with, say, 50 statement variables, then there would be 2 to the 50th entries in the truth table. That becomes very difficult to deal with very quickly, so later on we'll want to develop better techniques. Okay, so here's the truth table in all its glory written out in lecture slide form. So that is it for this lecture. I strongly suggest you read pages 11 through 17, and in particular you look at the proofs for claim 1, which we actually do in the lecture slides, and then claims 2 and 3, to see a couple more examples of proof by truth table. I hope all of you have a wonderful day, and as always, if you have any questions, feel free to ask on Piazza or attend office hours or tutorials.